To Lecture 10. In this lecture, we will introduce the concept of moment-generating function, and after that, we will make use of the idea of moment-generating function and then derive a bound called Chernoff bound. Let's start. So the moment-generating function, short name MGF, for a random variable x is defined to be a function mxt, whose value is equal to the expected of e to the power tx. Now, how do we interpret this term? So for a fixed value of t, let's say t is equal to 0.1, then e to the power 0.1x will be a random variable. And because it is a random variable, we can talk about the expected value. And the expected value of a random variable will be a constant, a fixed constant. So in that case, by varying the value of t, we will get different values of expected of e to the power tx. And this gives us a function of t, and this is called the generating function, the moment generating function. As we shall see, the moment generating function of x can produce all the moments of x. So recall what is a moment. So e of x, the expected value, is the first moment, e of x squared is the second moment, and so on and so forth. So the MGF of x, we will see that it can produce all the moments, e of x to the power k, for all positive integer k. So this is the theorem. So for all integer k greater than or equal to 1, let's say we use mx bracket k of t to denote the kth derivative of the moment generating function. Then we can obtain the kth moment by first differentiating the moment generating function k times, so we get a kth derivative, and then after that we set t to be 0. And for the assumption, we will need a slight assumption that in the process of deriving this theorem, we can exchange the expectation and differentiation operands in the calculation. So we will see soon what does it mean. And this assumption is not generally true, but then for all the random variables that we are studying in this class, then this assumption is valid. So in the next page, we are going to show the proof of this theorem. Okay, so recall that what is the kth moment, or how the kth moment is derived. So we first make differentiation on mxt k times, so differentiate k times, and then set t to be equal to 0. Okay, now the proof is like this. Okay, so the moment generating function is expected value of etx. So the first derivative is we are trying to differentiate this function. Now here we assume that to differentiate the whole function, it is the same as to compute the expected value of the differentiation of the middle part. So we can exchange the order of doing expectation and differentiation. Is that okay? And then if it is like this, then the middle part, recall that we are doing differentiation with respect to t. T is the variable. So in that case, the big X here will be a constant with respect to t. So when we differentiate e to the power tx, we will get x times e to the power tx. And similarly, if we differentiate this one more time, then instead of x here, we will now have x squared times e to the power tx, and so on and so forth. So in general, if we differentiate the moment generating function k times, we will get this is equal to the expected value of x to the power k multiplied by e to the power tx. Now this is the kth derivative. So by setting t to be 0, then what will happen? When t is 0, so we put t to be 0 here, e to the power 0x will be equal to 1. And in that case, this will give us expected value of x to the power k as we want. So we see that by doing differentiation on the moment generating function repeatedly, we can get the moments one by one. Okay, so let's see an example. Suppose that x is a geometric random variable with parameter t and p. Then, based on the definition, the moment generating function of x will be a function of t in this form, so it is equal to the expected value of e to the power tx. Now, what is the expected value of this one? So we will see that x can take on value of 1, 2, 3, 4, and so on and so forth. And when x takes on the value of 1, then this value is e to the power t. When x takes on the value of 2, then this value is e to the power 2t, and so on and so forth. Now, to get the expected value of this term, we will weight et, e2t, e3t, and so on and so forth by the corresponding chance for this to happen. So there is chance p, probability p, for the value of x to be 1. So we will multiply e to the power t by p, and then there will be probability p times 1 minus p such that the x value is equal to 2. So we will multiply e to the power 2t by the value of p times 1 minus p, and so on and so forth. And then this term, we can now do some simplification by taking the common factor p times e to the power t outside. The first term becomes 1. The second term becomes 1 minus p e to the power t, and then the next term becomes 1 minus p squared times e to the power 2t, and so on and so forth. And this latter part is an infinite sum, so we can apply our infinite sum formulas that we have studied in lecture 5, so that we get this is equal to p times e to the power t divided by 1 minus this factor, 1 minus p e to the power t. So we get the moment generating function. Now let's do something further. Okay, now this is a moment generating function. I just copied it from the previous page. So let's try to differentiate this function with respect to t. So after the differentiation, this is what we get. So this is actually simple. We obtain this by using the chain rule. So first of all, I differentiate e to the power t, and then keep the other parts unchanged. And then the next term here is I differentiate 1 over 1 minus p times e to the power t. So I differentiate this part while we keep p times e to the power t unchanged. So this is how we derive this term. So you can work it out by yourself. Now we get the first derivative. Now let us set the value of t to be 0, and we will see something amazing going to happen. So when t is equal to 0, et, e2t, et here are all 1. So in that case, this term, the first term, will become p divided by 1 minus bracket of 1 minus p. So it is p. And similarly, this term, the second term here, will be p times 1 minus p multiplied by 1, so it's gone, divided by p squared. So if we make the two terms to have the common denominator p squared, the first one will become p squared. The second one will become p minus p squared. So after simplification, we get p divided by p squared, which is equal to 1 over p. And this 1 over p value is exactly the same as the expected value of x for this geometric random variable. So this is an example of showing that once we know the moment generating function, we can use it to get the first moment and also the second moment, and so on and so forth. Okay, next, we will talk about a special theorem concerning to MGF. So this is called the uniqueness theorem. So let's see what it is saying. Suppose that we have two random variables x and y, and suppose that the moment generating function of x agrees with the moment generating function of y for a continuous period where t is equal to minus d up to d. So within this range of t, the two moment generating function agrees. Now just a small portion of them agrees would then imply the two random variables have the same distribution. So So this is called the uniqueness theorem. And the proof of this one is too complicated. So we will omit this here. And for interested reader, so you can take a course for something like advanced probability, and then you can learn why this is true. And probably you will need to have some kind of advanced calculus to help as well, or complex analysis. Okay, so this is too complicated, too hard to prove for this course. Now, another property of the moment generating function here is, suppose that we have two random variables x and y, and they are independent. So this is important, so they are independent. Then the moment generating function for the sum of these two random variables is equal to the product of the corresponding moment generating function. And the proof is actually very straightforward. So the moment generating function for x plus y will be equal to something like this. Because e to the power t bracket x plus y is equal to e to the power tx multiplied by e to the power ty, so we will rewrite this term in the middle part into this term. Now x and y are independent. And then if we know x, then we will know etx. If we know y, we will know ety. So if you tell me that x and y are independent, that means that given any information about x, I would not have any change about the view of what happens to y. So in that sense, given any information of x means that given any information about e to the power tx. So given any information about e to the power tx, we will not affect the view of what happens to e to the power ty. So in that case, e to the power tx and e to the power ty, these two things are also independent. Now because they are independent, so the expected value of the product of these two independent random variables is just the product of the individual expected value. And this expected value is the moment generating function of x, and this expected value is the moment generating function of y. So for a fixed t, we have this effect. So in that case, for every t, we will have mx plus yt is equal to mxt times myt. So this is very, very useful in later course. Okay, now we are ready to talk about Chernoff bounds. So Chernoff bounds will have the right tail form and also the left tail form. So right tail form bounds the probability of x greater than or equal to a value of a. And the left tail will bound the probability of x smaller than or equal to a value of a. So let's see what is the Chernoff bounds for the right tail. Suppose that x is a random variable, then for any t greater than 0, so this is important, any t, so t could be 0.1, could be 0.2, whatever. Then the probability of x greater than or equal to a is always smaller than or equal to the expected value of etx divided by eta. So when t is a fixed value, then this is a fixed value, and this is also a fixed value. So it is going to give us a bound. Now because this middle term, this middle formula here, the probability of this one, holds for any t greater than 0, so if you want to make a very tight analysis, then we will choose the t that gives us the tightest bound. So what is the t that gives us the tightest bound? We will choose the t such that the right-hand side is minimized. So consequently, we can write this whole thing as this one. So the probability of x greater than or equal to a will be less than or equal to the minimum of all the choice for t greater than 0 of this term. Okay. So why we call it bounds? It is because it holds for any t. So it is like we have infinite number of bounds, but then for most of the time, we will choose the bound that is the tightest. So we will find the best t so that the right-hand side, this part, is minimized. Now the proof is actually very simple. Okay, just a 3-line proof. So first of all, probability of x greater than or equal to a will be equal to the same as the probability of tx greater than or equal to ta for any t greater than 0, right? So we just so if x is greater than or equal to a, we multiply a positive term on both sides. We will still keep this inequality to be in the same direction. So this is equal. So x greater than or equal to a if and only if tx greater than or equal to ta. And next, this probability is the same as the probability of e to the power tx greater than or equal to e to the power ta. To see this is actually the property of e, or the property of e to the power x for a function of e to the power x. For a function of e to the power x, it is always increasing, because if we differentiate this one, this is still e to the power x. So it is always greater than 0, always increasing. So if x is larger than a, then tx is larger than ta, and then e to the power tx will be larger than or equal to e to the power ta. So we will have all of them the same direction. So this is again equal. So this happens if and only if this happens. Okay. Now finally, we will see that e to the power tx will be a random variable that can only take on positive values. So in that case, we can now apply Markov inequality. So this will be less than or equal to this expected value of e to the power tx divided by e to the power ta. Okay, so this is a very simple derivation. And now, how about the left tail? So left tail concerns with probability of x smaller than or equal to a. So this time, we will have the bound of the same form, except that we need to be careful. This time, the t that we can choose are those that is less than 0. So again, we will choose the best t to make this as tight as possible. So we will choose the t such that the right-hand side is minimized. So consequently, we get this bound. The probability of x less than or equal to a, this probability will be less than or equal to the minimum of all choice of t, but this time t is less than 0 of the right-hand side. And the proof is just like a one-line change. So we begin with probability of x less than or equal to a. Now we now see the effect of choosing t less than 0. When we choose t to be less than 0, then multiplying t on both sides will now change the direction of this inequality. So smaller than or equal to becomes greater than or equal to. And because this is still greater than or equal to, this happens if and only if this happens, because it doesn't matter whether the number is negative or positive for tx greater than or equal to a to imply etx greater than or equal to eta, and vice versa. Now, because we have the same form here, we will apply the Markov inequality in the same way, so we get the same format of the right-hand side. So the right-hand side is of the same format, but then notice that this is important. So the choice of t is now restricted to those that is less than 0. Okay, so there's a final remark. Okay, so previously we have introduced the Markov inequality, the Chebyshev's inequality, and now we have the Chernoff bounds. Now for Markov, we will make use of expected value. And for this Chebyshev, we will make use of expected value and the variance. So this is equivalent to, we are making use of expected value of x and also the expected value of x squared. So the first moment and the second moment. And now Chernoff. So although we didn't write down this moment generating function m here, but this is the moment generating function. This is the moment generating function, right? So for Markov and for Chernoff bounds, we are making use of the moment generating function, and moment generating function captures all the moments. So we have e of x to the power k for all k when we are applying the Chernoff bounds. So in that case, because it is using more information, so in general, Chernoff bounds will give us a much tighter bound than the other two. So that's all for lecture 10. Thank you.